this episode, we tackle supply chain risk, which is one of the most important and misunderstood topics in modern security architecture. When people hear supply chain, they often picture shipping boxes and physical parts. But in cybersecurity, it usually means the components, services, and dependencies you rely on to build and run systems. That includes software libraries, vendor products, cloud services, managed platforms, and even the tools used to build and deploy code. The hard part is that supply chain risk is real and can be severe, yet teams still need to deliver features and keep operations running. So the goal cannot be to freeze change or block everything unfamiliar. A good security architecture approach reduces the chance that a compromised dependency harms you, and it reduces the blast radius if something slips through. The exam often tests whether you can balance security controls with delivery realities, because a design that cannot be adopted does not protect anyone in practice. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. To understand supply chain risk, start with the idea of inherited trust, because the supply chain is basically a long trail of trust decisions. Every time you use a third-party component, you are trusting that it is not malicious, that it was built securely, and that it will behave as expected over time. The challenge is that you rarely have full visibility into how a dependency was created or maintained, and you may not even realize you have a dependency until something breaks. In software, dependencies can be direct, like a package you knowingly include, or transitive, meaning a package pulls in other packages that you never chose explicitly. In services, dependencies can be hidden behind a provider's architecture, where your application relies on systems you never see. Supply chain risk is the risk that this inherited trust is misplaced, intentionally through compromise or deception, or accidentally through weak practices. Security architecture treats inherited trust as something to manage carefully rather than something to accept by default. A common misconception is that supply chain risk is only about malware, but it includes a wider set of failure modes. A supplier might be compromised and distribute a harmful update, or a dependency might include a vulnerability that attackers exploit at scale. A vendor might discontinue support, leaving you stuck on outdated versions, which becomes a security problem because patching becomes harder. A provider could change behavior, deprecate features, or alter logging and monitoring capabilities in ways that affect your detection and response. Even a simple misconfiguration from a supplier can cascade into your environment if you rely on their defaults. The supply chain is also a target because attackers can compromise one supplier and then reach many customers, which makes it efficient for them. Architecture must therefore plan for the possibility that trusted components can become untrusted without warning. Now we turn to the balancing act in the title, which is managing risk without slowing delivery and operations. If security tries to solve supply chain risk by banning third-party components or requiring endless approvals, teams will work around the rules, and you will end up less secure and less visible. The better approach is to build guardrails that are predictable, automatable, and proportional to risk. Predictable means teams know what is expected and can plan for it, rather than discovering requirements late. Automatable means the checks happen consistently as part of normal workflows, reducing manual bottlenecks. Proportional means high-risk components get more scrutiny, while low-risk components are handled with lighter controls. Even though we are not discussing tools, the principle is that security should behave like a quality system, not like an unpredictable gatekeeper. When guardrails are designed well, delivery continues and risk decreases because fewer unsafe choices make it into production unnoticed. A foundational architecture control for supply chain risk is dependency visibility, because you cannot manage what you cannot see. Visibility means knowing what components you rely on, what versions you are using, where they are deployed, and what they do in the system. This applies to code libraries, container images, vendor appliances, cloud services, and even build tools and scripts. Without a clear inventory, you cannot assess impact when a vulnerability is announced, and you cannot prioritize fixes effectively. Architects often encourage a single source of truth for dependencies and system components so teams can answer questions quickly during incidents. This is not about creating paperwork. It is about reducing uncertainty when the environment changes. In exam scenarios, the correct direction often involves improving visibility and traceability rather than guessing or relying on memory. Once you have visibility, you can apply risk-based acceptance, which is the idea that not every dependency deserves the same treatment. Some components run with high privilege, touch sensitive data, or are exposed to the internet, which means their compromise would have high impact. Other components are isolated, low privilege, or used in non-critical paths, which may lower risk. A risk-based approach also considers supplier maturity, update practices, support history, and how quickly issues are disclosed and fixed. You do not need perfect information to do this. You need a consistent way to rank dependencies and decide what controls apply. For high-risk dependencies, you might require stronger evidence of integrity, stricter version control, or more careful rollout and monitoring. For lower-risk items, you may allow faster adoption with standard checks. This keeps security aligned with delivery because it focuses effort where it matters most. Integrity and authenticity are central supply chain concepts because many attacks involve substituting a malicious component for a legitimate one. Architects aim to ensure that what you build and deploy is exactly what you intended to use, not something altered in transit. This includes controlling where dependencies are obtained, reducing exposure to untrusted sources, and ensuring changes are deliberate and reviewable. It also includes ensuring that build outputs can be traced back to inputs, so you can answer how did this get here when something suspicious appears. When integrity is treated as an architecture property, you design systems that resist tampering and provide evidence when tampering happens. This is especially important in the build and deployment pipeline, because if attackers compromise that pipeline, they can inject code into products that appear legitimate. Exam questions may test whether you understand that the pipeline itself is part of the supply chain and must be secured as a critical asset. Change management is another place where supply chain risk and delivery speed collide, because updates are both necessary and risky. You need updates to patch vulnerabilities and fix bugs, but updates can also introduce new vulnerabilities or unexpected behavior. Architecture can help by designing for safe change, meaning changes can be tested, rolled out gradually, and rolled back if necessary. A safe change design includes clear versioning, controlled deployment stages, and monitoring that can detect abnormal behavior after an update. This approach allows you to patch quickly without gambling the stability of the system. It also reduces the temptation to delay updates out of fear because you have a controlled way to adopt them. In supply chain scenarios, the best answers often involve improving the safety of change rather than avoiding change altogether. Another key concept is reducing blast radius, because no matter how good your controls are, you should assume something will eventually fail or be compromised. Blast radius reduction means designing systems so that a compromised component cannot easily compromise everything else. This includes segmentation, least privilege access, strong authentication between services, and careful control of secrets and credentials. It also includes limiting what a component can reach, what data it can access, and what actions it can perform. If a third-party library is exploited, the attacker should face barriers that prevent them from moving laterally into other systems or escalating privilege easily. This is a classic architect mindset: assume failure and contain it. The exam often rewards designs that anticipate compromise and limit its impact rather than designs that assume perfect prevention. Monitoring for supply chain risk is also distinct because you are watching not only for external attacks, but for unusual behavior inside trusted components. If a component suddenly makes new outbound connections, accesses unexpected data, or behaves differently after an update, those signals can indicate compromise or misconfiguration. Architecture can support this by defining what normal behavior looks like and ensuring that key events are logged and observable. You can also design alerting around changes to critical dependencies, because unexpected changes are often more meaningful than routine operations. This is not about watching everything all the time, but about choosing observability points that give you early warning. The goal is to catch issues before they become large incidents and to gather enough evidence to respond quickly. In exam terms, The best choices often include both preventive controls and detection controls, because supply chain risk requires layered defense. Supply chain risk also affects procurement and vendor selection, even though that can sound like a business function rather than architecture. An architect often contributes by defining security requirements for suppliers, such as support expectations, transparency, update practices, and reporting behavior. These requirements become part of selection decisions and can prevent high-risk suppliers from being adopted in the first place. They can also set expectations for evidence, such as receiving security reports or having clear incident communication processes. The important point is that architecture is not limited to diagrams. It includes setting technical and assurance expectations that shape what components are allowed into the environment. If you let procurement choose solely on cost and features, you may inherit risk that is expensive to mitigate later. When security expectations are defined early, delivery is not slowed, because teams avoid adopting problematic dependencies that would cause rework. A practical mindset for learners is to treat supply chain risk as a continuous activity rather than a one-time approval step. New dependencies appear, old ones get updated, suppliers change ownership, and vulnerabilities are discovered regularly. That means your architecture should support ongoing visibility, ongoing evaluation, and ongoing response, not just a gate at the beginning. This can include periodic reviews of critical dependencies, regular checks that suppliers still meet expectations, and rehearsed response actions for high-impact scenarios. The idea is not to create bureaucracy, but to create a steady flow of assurance that keeps pace with change. When assurance is continuous, it becomes part of normal operations, which is how you avoid slowing delivery. Continuous thinking also aligns with the reality that attackers evolve, so a dependency that was safe last year may not be safe today. To conclude, architecting for supply chain risk without slowing delivery is about building smart guardrails that manage inherited trust in a way teams can live with. You start by gaining visibility into dependencies and treating the build and deployment pipeline as part of the supply chain that must be protected. You apply risk-based controls so scrutiny matches impact, and you focus on integrity, traceability, and safe change so updates can happen quickly and safely. You design for reduced blast radius, because containment matters when prevention fails, and you support monitoring that can detect unusual behavior in trusted components. You also shape supplier expectations early so risky choices are avoided before they become expensive. When these ideas come together, security becomes an enabler of reliable delivery rather than a blocker, and the system becomes more resilient to one of the most common and scalable attack paths in the modern world.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.